So today we are going to do an example problem in reacting balances. And so I wrote a spreadsheet to go along with this, so hopefully I don't have any issues connecting the computer. Otherwise you'll be staring at me for a while. But I wrote sort of I would say an arbitrarily, so fairly, not arbitrarily complex, but a pretty complex energy balance reacting system to show how if we build a spreadsheet really well, it's not that bad to do an energy balance on any process regardless of how complex it is. So this is a big example. All right, so this is propylene oxide synthesis. Propylene oxide. So we have propene, C3H6, so it's got one double bond, plus oxygen goes to our propylene oxide. But we have some side reactions. So in this case, we could inadvertently burn our propene. And we can also have incomplete combustion. Okay, so essentially, based on this system here, we'll have material flowing in, we'll have material flowing out. We want to know what is the total amount of heat going in or out of this process, and then we can play around with some of the parameters and whatnot. So the conditions are going to be 1 mole per second of propylene. We're going to say 100% excess O2. This is going to be entering at 25 degrees C. The oxygen is going to be entering at 200 degrees C. And this can come from either O2 or air. We're going to solve it both ways. The outlet, we're going to say is 700 degrees C or adiabatic.
When you say or, you just say it's for
We're going to solve it twice. Yeah. But once we have the spreadsheet built, it's all going to be nice and easy, and we can play around with the variables. Okay, I'm going to call this reaction 1, reaction 2, reaction 3. So we need some information on the material balance before we can attempt to solve the energy balance. So I'm going to call extent of reaction 1 as 0.65 moles per second, extent of reaction 2, 0.1 moles per second, and extent of reaction 3, we'll say 0.05 moles per second. This is significantly more complex than any of the homework problems that we have on this week's assignment. So, step 1. We need to collect our material property data. So in the Felder book, and for data, we require the heat of formation and the specific heat for every species in the system. In the Felder book, I was fortunate to be able to get the propylene, the oxygen, the nitrogen, the CO2, and the CO and the water. That has all the information we need. This is all for gas phase process as well. But for the propylene oxide, I had to go to the NIST webbook. So here I wanted to take a little bit of time and talk a bit about what we can do based on the information we have provided. So in the NIST webbook, the heat of formation is given from two literature references. One was minus 94.7 plus or minus 0.6 kilojoules per mole. And it also gave a different value of minus 117.1. Without digging further into the actual papers and which one I trust the most, we could actually solve the problem both ways. But when we're working with real systems and real data, there is going to be a limitation based on the reliability of the results. Right? These are all based on experiments. Right? We don't have a great unifying theory that allows us to predict these things. So the quality of the data is going to impact the quality of our energy and material balances. Now the C sub P was tabulated from 100 Kelvin, all the way down to 3,000 Kelvin. Seeing as I put this together last night, I wasn't super keen on entering it in manually and doing a correlation fit. But the data here that I found in the NIST webbook, I would fit it to a polynomial of the same form as what is typically used in the Felder book, and that's how the correlations in the Felder book are obtained. They take tabulated data, fit it to a polynomial function, and then give us the coefficients of those polynomial fits. I could have done the same thing for the propylene oxide, but instead I decided we're just going to say a constant value at 500 Kelvin. And at that value, the number was 110.99 joules per mole Kelvin. Okay, so step 2, let me put down the rest of the steps here, and what we're going to be talking about, and then I'll walk you through how I built my spreadsheet and how we can solve this problem. So step 2 is build our sheet. Step 3, perform our material balances. And step 4, and this is where we do our energy balance. In this case, I'm going to do the heat of reaction method. So for this example here, Q, the rate in or out, is going to be the enthalpy out of the system minus the enthalpy in the system. And this is just a simple rearrangement of keeping track of the in and the out. Yes?
Why did you choose to do the heat of reaction method?
Heat of formation method.
Oh, okay.
That is by far and away my most preferred approach.
Okay, I guess I just misheard. I thought you said heat of reaction.
Oh, sorry, no. So just to clarify, so if you can do the heat of formation method, I always recommend the heat of formation. But there are some circumstances for maybe some complex systems or some macromolecules where we don't have access to the formation energy, and then we have to do the reaction method. Question?
You could have still used it though, because you do have your set of reactions still for this one.
Well, I could, yeah, for sure. Yeah, I absolutely could have, but I would have needed to have calculated the standard heat of reaction for each of these and had to add all this in. But we'll see when I get my spreadsheet pulled up that you can see why it's much, much easier to do the heat of formation method. Okay, so bear with me a little bit, see if I can get this thing fired up. So the video here is not going to be phenomenal because I'm going to project the computer screen over there so I can still have access to talking about this. But since you're all in class, you get the full experience. All right. All right, you guys see that. How do I get rid of the ribbon? So, here is my spreadsheet. So let's walk through this a little bit. You guys can see that all right? So what I have done, and this is the same template for like the cell formats that I have uploaded onto Canvas, right? I have an input cell where it's kind of like a diagonal lines with blue, calculated is just a gray background, and then for constants, and I'll break down again why I do it this way, some vertical lines but with black text. So it's somewhat identifiable, which is an input-output. Now when I do this on my own, I just usually use colors, but I reformatted this here for the class because it works better printing it black and white. So what I did is I have constructed my data table. And I format it so that I have the heat of formation of the liquid, A, B, C, D, heat constant, so heat capacity constants. Now you'll notice here that I reconstructed the table exactly. In the Felder book, the A is times 10 to the 3, the B is times 10 to the 5, 8, and 12. Now the reason why I did this is because now I can very easily compare the numbers that I entered into my table to the book values. So if I think I made a mistake, if I ever want to troubleshoot this table, all I have to do is compare a number in the book to the number in my spreadsheet. I don't have to worry about, oh, this one says 10 to the minus 8, but the book says 10 to the 9 because it was, gave me 11 and not 1. So it makes things a lot easier. I don't have to think. I just look at the number. I look at the number. Are they the same?
Does the thinking for
Good.
you.
Yeah, I didn't screw up. But if I were to try and put in, for example, this one here, 559.58 times 10 to the 3, right? Times 10 to the minus 3, the number that Excel would tell me would be 5.95 times 10 to the minus 2. And that's not super easy to compare to 59 in the book, right? They seem totally different even though they're the same number. So, all of my components in the system. Now the order that I put them in here doesn't matter when I set it up. I kind of did it so that these three components here, the 1, 2, 3, those were the primary species that were interested in the reaction. And then here's all the secondary stuff. And then lastly, I put nitrogen at the bottom because it's an inert. It doesn't participate in the reaction. So this part here, I format it. So when I look at my spreadsheet instantly, I see, these are constants. I don't have to troubleshoot these other than make sure I didn't screw up the constant. So that's been entered. Now, here is my section of the spreadsheet where I actually do all of the calculations. I have exactly the same organization here, and it will make sense why we do that. I have a reference temperature and all of my design specifications in one location. So if I can change anything I want, so I could change this to 1,000 degrees C output, right? And everything automatically updates and solves just fine, right? This one here, I put 1 if it's air and 0 if it's oxygen. So if it's pure oxygen, you see that the nitrogen term goes to 0. If it's 1, it doesn't go to 0. So just little programming tricks like that to make it work well for a demonstration. So how I build my spreadsheet is just really algorithmic, and I just basically march through the process as if we're going from start to finish. So I enter in my flow rates. Propylene, I have 1, right? That's our basis. We have 100% excess oxygen. So if I go to this gray colored cell, that's telling me that this is a formula that I entered in that accounts for the reaction. So if I wanted to be a little bit more elaborate, I could change this to an actual stoichiometric coefficient term. But basically, I'm adding in the 100% excess. And for inputs, I have nothing else going on here. And then for the nitrogen, this is my little clever formula where it goes to 0 if it's pure oxygen, basically by just timesing it by either 1 to change nothing or 0 to get rid of everything. Simple enough. Now, this next column here is for the mole fractions. Why would I care about the mole fractions in a reacting system?
Wouldn't it affect the extent of reaction?
Not the extent. The extent just tells us how much we go from here to there. The extent doesn't necessarily care about the mole fractions, but we've done other problems in this class where the mole fraction really matters for a reacting system. Why?
Is it because the sum of all the mole fractions has to equal 1?
Well, I've confirmed that it does down here. That's a double check that I built into the spreadsheet. Right down at the bottom, it adds up to 1.
Oh, okay.
What's a situation where the mole fractions really matter?
Two ways.
What was that?
2 ways. I don't know.
Okay, sorry, I can't hear you guys.
So saturation argument.
Correct.
Or you-
What field of study does phase equilibrium fall under? Exam 2 content all was thermodynamics, right? Multi-component equilibrium thermodynamics. What about reaction thermodynamics?
Was it just like how fast it reacts? Is that
So that would be kinetics, but thermodynamics will tell us how much is theoretical based on the equilibrium constant, right? Like an acid dissociation constant. So in this spreadsheet here, if I'm calculating the mole fractions, I could also add another layer onto this and have it to be an equilibrium calculation as well, right? Where I could modify these 3 extensive reactions based on their Ka equilibrium constants. So if you have a problem where you have to not only do the energy balance, and as the temperature changes, the equilibrium constant changes. As the equilibrium constant changes, the extent of reaction changes. As the extent of reaction change, the heat requirements change. So all of these are tied together. So eventually by the end, on the last homework problem, you're going to have a question where you have to do the material balance, the energy balance, the equilibrium, all together at the same time to find out what the system would actually go to. Right? Integration of mass, heat, and thermo all together. In this particular problem, we don't care. We don't really need to worry about the mole fraction. But if we did, right, if we had an equilibrium constant here, the equilibrium constant for this reaction, for an ideal phase reaction, would be the mole fraction of the propylene oxide divided by the mole fraction of the propylene divided by the mole fraction of oxygen to the 1/2 power. So if we wanted to calculate an equilibrium constant, we could. Or if we needed it to determine our extents, we could. So that's why I built a spreadsheet this way. Okay, now I have another column here for the temperature in. Everything is coming in, well, 2 things, right? You have 25 for the propylene, and then for the oxygen is 200, and then I just put 0 because there's nothing of those other things. So, now we get into the meat of the problem. Our enthalpy coming into the system following the heat of reaction method is given by this big, long, unfortunate equation. But if we scroll up, we can see that the form makes a lot of sense. I don't know why the color keeps going away here. So, if we look at the equation, we have the blue B8, which is our heat of formation. So we are creating our compound. And then all of this other stuff here, this is the heat capacity. And I don't know of a better way to do this than just to have a big long equation like this. But here's the good thing about it. I formatted this as gray, which means that when I verify and troubleshoot my code, I only have to double check the equation. And if we look at the format here, we have red, which is the A coefficient times by that 10 to the minus 3. Right? Let's quickly go through and double check the other ones. Times 10 to the minus 5, times 10 to the minus 5, times 10 to the minus 8, times 10 to the minus 12. Okay, well, I got that part fixed right. Now let's check the other ones here. Purple and green, purple and green, purple and green. Those are my reference temperature and my inlet temperature. Right? So down here, all of those individual ones, they all make sense, right? I'm going from my reference, which is the green, all the way up to my actual system conditions. So that was really easy to troubleshoot. So ultimately, it looks like a big old mean nasty equation, but it's really not too bad. Because if you break it down into those individual steps that you're troubleshooting, it all works out quite well. So now in Excel, you can copy the same equation. Now, you see how it's a white cross here, and now it is the black cross? If I just drag it down, I copy the same formula. So if I go to the CO2, for example, I locked in position the reference temperature with the dollar signs, and in Mac it's Command T, and I think in Excel it's like, in Microsoft it's F4, is that right? Yeah. So, but if we scroll up then, by having everything formatted in exactly the same way, I can just go to any single equation I want to, right? Let's say for the water, I grab all the water coefficients. For the nitrogen, I grab all the nitrogen coefficients. And for the oxygen and nitrogen, I just have zeros for my heat of formation and my heat capacity constants. Right? Next, to make things easy, right, this column here is the specific enthalpy, right? This is the heat per unit mole, which is what we're calculating in the heat of formation method, right? Just to be clear, my H cats are in kilojoules per mole, and this is equal to delta H of formation plus integral from 25 to T C sub P of species I dt. Okay. All I've done is code that into my spreadsheet here. Now, but this is not what I really care about. What I really care about is the summation of the flow rate times by the specific enthalpy to give me units of energy. Because in my energy balance, everything has to be units of energy. So this step here, all it does is multiply the flow rate times by its specific enthalpy, and then of course it's the same exact formula going all the way down, and at the end, I just add it all up. So this cell right here, F34, is this term right here, F34. Any questions so far about why I did this particular way? Next. Okay, so that is taking care of all the energy coming into the system. So now I just need to figure out all of the energy going out of the system. To accomplish that, I need to balance my material balance for all of the chemical reactions. So, I have my reaction extents that are based on my design specs. Now this might be given to you on an exam in a different way. You might be given conversion or yield or selectivity. But if you can work your way back to calculating the extensive reaction, that's going to be the easiest way to implement the solution. Overall, I would say, if you had a choice. So what I did is I entered in here all of the stoichiometric coefficients for all of the different reactions. So let's go through reaction 1 first. Stoichiometric coefficient for propylene is -1. I just entered a -1 when I covering it up. For oxygen, it is -0.5, and for propylene oxide, it is 1. For the combustion reaction, I am consuming 1 propylene, so it's -1. I am consuming 9/2 oxygen, and you'll notice if you look at the bar on top, I didn't actually enter in, I actually just typed in directly equals -9/2. One extra step that I can't screw up. And then we're creating CO2 and water, and they both have stoichiometric coefficients of 3. And then, of course, I did the same thing for the incomplete combustion reaction. Now, why I do this is then when I enter in my formula for calculating the outlet flow rates, it's all the same. I just have to double check one equation. It's not every single cell is its own equation with its own unique little function, its own unique little troubleshooting problems. Right? I'm very lazy when I do these calculations. So if it takes me 30 extra seconds to write one uniform formula for everything, that saves me a ton of time on the back end troubleshooting it. Because let's say, for example, for propylene, I entered in its extent of reaction material individually. Then I have to have an individual one for oxygen, right, because it's participating at a different rate. I have to have an individual one for propylene oxide, individual one for CO2, individual one for water, individual one for CO. So if something went wrong in my code and I wanted to double check what I screwed up, I'd have to click on this one. Oh, let me check that equation. I click on this one. Let me check that equation. I click on this one, so on and so forth, right? Most all of your time is always going to be spent on troubleshooting. Solving a problem exactly correctly from start to finish the first time is never going to happen. So especially when you're doing any sort of coding involved work, most all of your time is going to be spent troubleshooting. So if you can build your program, your code, organize your work so that troubleshooting is easy, you will be able to solve problems a lot more quickly. And building the spreadsheet this way allows me to troubleshoot it very, very quickly without hardly any effort at all. So in order for me to verify all of this big complex calculations, what I need to do, I need to check that I've entered in my numbers correctly. That's pretty straightforward. I need to check that I've entered in my design specifications correctly. And for most all of these cells, it's just one equation. Right? The inlet here, obviously, there's some trickery I played around with there, but in theory, you could do that on the front end, manually calculate it and put those numbers in there. But I wrote it this way to be a little bit more robust. This mole fraction equation, that's the same one, right? Mole fraction of propylene divided by the total number of moles. Double checked all of that. And these are all exactly the same equation. Enthalpy, all exactly the same equation, all the same equation, all the same equation. So I really only have to check 3 or 4 equations to troubleshoot this entire spreadsheet. And same thing on the back end here, of course, right? Mole fraction, pretty straightforward to calculate. And I also add in these double check consistencies. If that doesn't add up to 1, then I've screwed something up. Sometimes when you add a row or subtract a row, maybe your equation won't capture that new one. But so when you add in these double check consistencies, then you have another way to verify that things are going well. Enthalpy final is the same equation, right? But the difference here is that I'm pulling it all away from one single final temperature cell value, as opposed to on the inlet. Here I have individual temperature flow rates in, but the outlet I'm just saying it's one combined flow rate out. Now, when I'm doing an energy balance, and this is something you may have to do for project part 2, you don't have to do an energy balance over a single unit operation. You can do an energy balance over an entire process. And if you were to do that, you might have different streams coming out in different phases of matter at different temperatures, in which case I should probably have added in a column here for the temperature outlet of each different material. But since this is just a single reactor, I kind of cut that corner and I just put one single location for the temperature. But every single one of these equations is the same equation. And it draws on having the fact that everything is organized nice and consistently. And then lastly, I calculate the enthalpy out, which is this term here. I add it all up, which is this bottom one, the minus 53.2 kilojoules. I had this kilojoules per hour. I didn't change that. It should be kilojoules per second. So now I want to solve for Q. So all I need to do is take all of the enthalpy out minus all of the enthalpy in, and I have balanced my process. And that's exactly what I've done here. I have taken the blue, which is the out, minus the red, which is the in, and my Q is 98 kilojoules per second for this process here. Q dot is equal to 98 kilojoules per second. Questions? Yes?
Where's your heat of formation?
The heat of formation, I built it into the table up here.
Okay.
So I have them all entered in. And I just put it where the heat capacity units were. And if, let's say, for example, you had a little bit more complex of a process where you had to deal with a phase change, what I'd recommend is I would just shift all of these over to the right, and then I would add in another column for delta H of vaporization. And it might be a little bit, depending on the problem, you might have to modify this a little bit. But this is obviously for a straightforward all gas phase process, where we have the heat of formation of all the components in the gas phase. But you could see if you modify it a little bit, you could sort of make it a bit more modular for more other systems. Yes?
How long does it take you to make an Excel sheet like this?
Like this? Oh, I've been doing it for a while though. Not too long. For me, I built this off of something that I had already built. Start to finish, you could do this probably half hour, 45 minutes. Not too bad, if you don't make any mistakes, right? So that's why the troubleshooting is going to be the big issue. So what I would really recommend for this week's homework is to build a really good, robust spreadsheet for one of the problems, and then you can modify it for each of the subsequent ones. Because then once you've solved one reactant system energy balance, as long as it's all gas phase and straightforward, you should be able to solve all of them. Yeah, and I want everything in this class to seem automated and algorithmic. Because as you progress through the program, the problems are going to get more and more complicated. So the material balance and energy balance aspect has to be something that you can just sort of come up with really quickly. And there's a question in the back, too.
Is there a way to, like, so you have your table all built, you're happy with it. Is there a way to just lock all those cells so you can't accidentally screw it up?
You probably can. You mean like if you like just change the number or something like that? Like I could just put 6?
Well, like, so on the table where you have all your equations.
Oh, here. You probably can lock cells. I've never done that with Excel. Yeah, I've never bothered. Oh, one other thing that I wanted to mention here, on the propylene oxide, we have, here, right, I grabbed one value of the heat capacity. And so in order to simulate that it was a constant heat capacity, I just put these higher order terms set equal to 0, right? Because the correlation in the book is that C sub P as a function of T, right? Now we most often integrate the heat capacity, but in reality, this is just the heat capacity correlation, right? This is the heat capacity as a function of temperature is equal to some A coefficient plus B times T plus C T squared plus D T cubed. So if I wanted to know what is the heat capacity of some compound at some temperature, I don't integrate this expression. I just put the temperature units inside of there. Okay? So in the case of propylene oxide having a constant heat capacity, if I only give you a number for A, that means it's no longer a function of temperature because this, and this all go to 0. Now the only trickery here involved is to make sure that I know that these units here are, for example, joules per mole Kelvin, or whatever the case is, to make sure the units work out. And in this case here, I believe the correlations in the back of the book are actually kilojoules per mole Kelvin. And so when I entered it into the spreadsheet here, right, it's a, where is the number here? Yeah, 110.99 joules per mole Kelvin. So the correlation in the back of the book is kilojoules per mole Kelvin, but it's times 10 to the minus 3, which the units all work out then. It would be 0.1 kilojoules per mole Kelvin or 110 joules per mole Kelvin. So just make sure the units work out. But that's a little trick that I threw in there to modify this. Now let's say, for example, I don't trust my propylene oxide heat of formation. Let's change it. Let's change it to the minus 117. So minus 117. How did that change our result? It's significant, actually. Pretty significant. It changed it to minus 113. So that could be a big issue, potentially. I mean, that's a fairly substantial change. That's a 10% or more difference just from having a little bit of uncertainty in one of our terms. Now I'm going to go back and undo that here. Oh, I actually have this at 1,000. Sorry. So it's 700 degrees C. Let's see. We have a different number there. So. But anyway, okay, so this is our spreadsheet here. Now let's go, for example, and say, instead, I want to solve this as an adiabatic process. Okay? So if I'm solving this as an adiabatic process, I'm going to say that these two terms here, the Q is equal to 0, which means that the enthalpy out has to exactly match the enthalpy going into the system. And this is no more difficult than just setting up a solver inside of my spreadsheet here. So I'm just going to go to goal-seek, because this is a relatively simple system. I want to set my Q equal to 0, and I will change the outlet temperature. And let's see if it works for me. Voila. Our Q is times 10 to the minus 7, and that means our outlet temperature comes to be about 1300 degrees Celsius. So what this is saying is that this process is a fairly exothermic process. So what I'm doing here is I'm taking all of the energy that's stored in the bonds of my feed material, I break all those bonds, and I reassemble them in a different way. All of that excess energy now has to go to one thing and one thing only, heating up the products. And the only way that those products can store the energy is for the temperature to go up. Now, let's redo this, but instead of having nitrogen in the system, let's change it to pure oxygen, and we'll resolve our goal seek. So the temperature go up or down? What do you think?
Way up,
Way up. Why would it go way up?
because you have a lot more oxygen.
Well, the nitrogen.
Same exact amount of oxygen.
Well,
The nitrogen
less
total
products.
because the nitrogen.
Yeah, so I have less total products, less total molecules, less total bonds that can absorb that energy in terms of rotations, vibrations, and translations. So I'll go to goal seek. I'm going to say my Q is equal to 0 again, and changing cell is here. 2200 degrees Celsius. Right, so the nitrogen in this case is really useful because it acts as a diluent. Right, it sucks up some of that energy. And so a lot of times in really exothermic processes, you will add in an inert just for that job itself. Ideally, in an ideal world, you would never want to do that. Right? If you had a perfect process, you would want to be able to heat something up to the conditions where you could best do the reaction, save as much energy of that as you could, cool it down by generating steam, and then send that steam somewhere else in the process. But by adding in a diluent, you're kind of sucking up a little bit of that energy. But for safety, it may be necessary, especially for really exothermic processes. Yes?
I think I just missed this, but you have that cell is like 1 is in air and 2 or 0 is in.
It's just a little bit of trickery that just made it easy. And
yeah,
so,
like where does that actually?
so what I did here is I have for my nitrogen flow rate, it takes in the amount of oxygen, and then this is just my standard unit conversion to go from oxygen to nitrogen and air, right? Times it by 0.79 divided by 0.21. And then I just added in this extra term here. If it's 0, then who cares? It all goes to 0. And then if it's 1, then I treat it as if it's an air coming in. So just a little math, a little programming trick to make it so I could just, on the fly, change it there. Yes?
And in this case, the way you built the spreadsheet, you could just say arbitrarily you wanted to supply half of it with pure oxygen and half with air. Would work.
I don't think my spreadsheet could do that condition, but I could very easily change that quite straightforward. Right? So if I did half, then what I would have to do is I would just say, divide that by 2, I think, right? That would accomplish the same task. So let's just say, for example, we did that. Tools, goal seek, set the Q equal to 0 by changing the temperature. And yeah, that's better. 1600 makes sense. Now, I do not have any concerns whatsoever if you want to use this sort of format in your own assignments. I will not, unfortunately, upload the exact spreadsheet itself, but I have no qualms whatsoever if you guys shamelessly copy the format that is done here. Right? The goal is to get everyone proficient in doing these calculations. But the difficult part is making sure that you build it right with all the formulas correct. So just having the format here, I mean, I think it's a useful format, and it's the way that I've structured it here is effectively the exact same way that most process flow simulators were structured. So if we were to do this, well, let's say the whole project in Aspen or Flowmax or whatever these commercial process flow simulators are. And these are something that you'll be playing around with a lot more in the junior and senior year as you're getting to bigger and bigger scale problems. What we're doing here is sort of the idealized understanding of how we keep track of the mass and energy balances. But the idea of the process flow simulator is that you are then going to be actively manipulating variables, actively reconnecting different streams from one location to the other. And so if you every single time moved a heat exchanger or changed the flow rate of steam coming into the system and you had to rebuild an entire mass and energy balance, that would be incredibly costly to your time and productivity. So the process flow simulator softwares, they basically have this all implemented algorithmically. And that's why we're trying to teach it so it seems like it's a really straightforward to implement algorithmic process, because it is, and the computers do that already. But if I build a chemical process, the first step is I tell my system what are all of the compounds that I'm going to be dealing with. And then what it does is it builds this table based on its database of material properties. And if it doesn't have the material properties, it tells you, I need heat capacity data, I need heat of formation data, or whatever the case is. I need heat transfer coefficient data. So the process flow simulators, the first thing they do is you tell it, I'm going to deal with propylene, oxygen, propylene oxide, blah, 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 blah. Right? And you tell it all the different things that you want to put into the system. Then every single stream, the software thinks, hey, there's a chance that there might be oxygen in this stream. There's a chance there might be water in this stream. So every single stream in the system has a possibility of having every single component in the system, which is exactly the same notion as building your table down here. Now, a lot of these, for the inlet, they're zero. They're boring. They're empty. But building the spreadsheet this way, I'm not paying for the real estate on my Excel spreadsheet. Right? I can make it as arbitrarily big as I want. The only penalty for having a really big, unruly spreadsheet means it's harder and harder to troubleshoot. But if I build it in a really uniform, consistent manner, then the penalty of troubleshooting it is much less severe and much less significant. Right? But I'm not paying by the cell on Excel. So if it makes my life easier and it's organized well, then absolutely that's what I'd recommend doing. Yes?
Sorry, so I haven't quite looked at the homework yet, but
Mm-hmm.
you could use the heat of formation for,
I think you can use it for all of them, but I think on some of them I ask you to do it both ways so that you have it in your toolbox. But on ones where it's not specified, it's up to you how you want to solve it. But this is why the heat of formation approach is so nice, because if we were to do the heat of reaction approach, we couldn't do it this way. We would have to, I'm sure you could come up with an equally competent cell or spreadsheet to do it, but you would also have to add in maybe, some standard heat of formation here, standard heats of reaction. You could basically, in this area here, compute, summation of stoichiometric coefficient of I times by the standard heat of reaction of I, right? And you can include this some other way in the system. So it's not going to be massively different approach if you were to do this in the heat of formation, heat of reaction approach as opposed to the heat of formation approach. But if you feel comfortable with what we talked about here, the homework should be pretty straightforward. Then the exam content should be pretty straightforward. The big difference, of course, right, is that on the exam, you don't have a computer, right? You'll have to do it by hand. So let's think about what that might mean in terms of what I'm going to ask you to do. Will you have a 4-term polynomial variable heat capacity on the exam?
please.
No, probably not. Could you have a 2-term variable heat capacity? Yeah, for sure. That's something I would definitely do, right? But I wouldn't make you do it like 20 different times, for example, right? I would just want to make sure that you can take any polynomial fit. All right, it might not be this form. I might give you a slightly different form just to see that you understand the concept of how we integrate heat capacities to get to delta H's. So you're probably going to be dealing with a system where you have constant heat capacities. But don't forget, we also talked about the non-reacting system balances are to some extent a little bit tricky as well, because then we have a lot more phase change operations and it's a little bit more nitty-gritty. Because the non-reacting system processes, that's where we typically have separations, changes in composition, changes in phase. Now it's definitely possible that I could give you a reacting system that starts off as a liquid and leaves as a gas. Right, and this spreadsheet here doesn't account for all of those conditions because you might have to throw in a heat of vaporization here or there, or you might have to deal with both the liquid and the vapor heat capacities. Questions? Do you have any other questions? I thought I saw a hand go up. Okay.
Oh, sorry.
So, yes, okay.
Yeah, sorry. So for the non-reacting, that's the non-reacting system.
Mm-hmm.
Isn't that just minus the delta H of formation?
Correct. So if we had a simple gas phase system, right, let's say, for example, we were preheating the airstream that goes into this process by cooling down the effluent, right? And this is something that would exactly what would happen. So if we have a reaction coming into the system, what we would do in practice is we would basically have the airstream be cooling down the, well, we move it directly into the reactor. right? So we would preheat our airstream with the hot effluent gas and then send that into the process. Right? That would be something that would be a smart decision to make in terms of energy efficiency. And if we were to do that, the energy balance on this heat exchanger would be from a gas phase that's hot to a gas phase that's cold. We could use our exact same spreadsheet. The only difference is that we would just have to change all of these stoichiometric coefficients to 0 because there would be no reaction. And we would just not consider the heats of formation. But you could, to some extent, use the same spreadsheet to do a non-reacting system as well. Or if you wanted to, you could go through and manually just change these terms here and delete that heat of formation. Right? Does that make sense? So for the non-reacting system, if there's no phase changes, then yeah, you could set up your whole calculation just as trivially as this one here. All right, so quiz on Friday, project due on Monday, exam a week from Friday. So nothing going on. Pretty easy time. See you later.